Welcome everyone, and today we will be hearing about SECDA-DSE, Automated Design Space Exploration of FPGA-based accelerator using large language model. We will be hearing from Jose Cano and Judaris from the University of Glasgow. So Jose is a reader in the School of Computing Science at the University of Glasgow, where he leads the Glasgow Intelligence Computing Laboratory. His work sits at the intersection of computing architectures, computer systems, compilers, machine learning, and security, with a strong focus on hardware-software co-design for efficient AI machine learning on mobile and embedded edge devices. While Jude is a postdoctoral researcher at the School of Computing Science at the University of Glasgow, where he completed his PhD on hardware-software co-design of FPGA-based neural network accelerator for edge inference. And his current research lies in the computer architecture with a special focus on hardware-software co-design of FPGA-based AI accelerator. So I would say, Jose and Jude, over to you for the presentation, and thank you so much.
Thank you very much, Christian, for the introduction. So it's our pleasure to be here today and present our project, SECDA-DSE. So along with, well, let me first of all introduce our research group, the Glasgow Intelligent Computer Laboratory. So we are part of the system section, or GLAS for short, within the School of Computing Science. And we do research at the intersection of three main areas, essentially computing system, machine learning, and security. So this is a picture from last year, and there are more people. We haven't taken an updated picture. But today we are going to present this project, and it's not only you and me. So we have also other PhD students, for example, Ricky and Virendra, and also an undergrad student, Mati, that I think they're all in the audience. So, well, this project is a team effort, okay? So essentially, this is the outline of our presentation. I'm going to introduce or motivate the need for a specialized accelerator for AI. Then I will talk a little bit about the previous efforts that we made, particularly you, that was the main developer of these three tools, the SECDA methodology, the SECDA-TF toolkit, and the SECDA-LLM toolkit. And then we will see how, using our previous efforts, we are proposing our new tool, SECDA-DSE, which is going to help in automating the process of exploring accelerators for a given target device. So I will introduce these 2 points, and then you will be talking about SECDA-DSE and its components, and describe also what is the current progress in the project and the next steps. And finally, I'll finish with some conclusions. So first of all, developing specialized or designing specialized hardware accelerators, for example, ASICs or FPGAs, can definitely make AI faster and more energy efficient. And this is very important, particularly, for example, on edge devices. So in general, but on edge devices, we know that we have less resources, and it's very important to kind of make the computation efficient, right? So in the case of FPGAs, we know that FPGAs are reconfigurable circuits that are more and more present in development boards. So we can find many boards for different types of application, including not only CPUs and GPUs and NPUs, also FPGAs, which gives us the flexibility or the possibility to provide specialized designs. What is the problem? Well, when we wanted to start to do this kind of specialized designs, we found that, developing accelerators using FPGAs is very time consuming, and there are 2 reasons for that. The first one is high-level synthesis. So if you want to generate the real circuit, well, without extending too much, but basically you need to synthesize the design that you have onto the hardware, and this requires time, right? And obviously you need to iterate several times since you have an initial design to a final design that performs as you expect. Okay. The second problem is system integration. Okay, we found that, well, it's not easy to actually integrate this development with existing frameworks like TensorFlow Lite or PyTorch or any other framework available. Okay. And more importantly, requires hardware expertise, right? So not everybody can start to design specialized accelerators for a given type of application. We found that architectural templates are widely used to simplify this design process, but still creating hardware templates is manual, right? So what we want in this project is to actually automate this part. The solution we propose is basically, as I mentioned before, based on some previous solutions and a new part. So first of all, we needed a design methodology that we call SECDA to efficiently reduce the development type of accelerators in general. then integrate this methodology into with widely used frameworks. In our case, we use TensorFlow Lite and LlamaCDP for LLMs, and I will show you later this integration. And finally, use some type of tool, in our case, LLMs, large language models, to efficiently explore the design space, right? So essentially, with that, we will be able to generate many hardware designs quickly and evaluate them using our previous tools. So without going into many details, the SECDA methodology essentially, SECDA stands for Consistency Enabled Co-Design of DNA Accelerators. So the idea is that if I have an accelerator here, representing this consistency, instead of doing hardware synthesis and synthesize the design into the accelerator and having this back and forth process, which, as I said, is slow and may require several iterations, what we're going to do is to do most of our development purely in simulation. So we are going to be iterating here, and maybe only a few steps, or ideally the last step, we will do the synthesis on the real hardware accelerator. Obviously, this requires that the simulation that we do here is accurate, and this was the main effort for developing this tool that was led by Jude. Right. So we have the methodology, so doing a lot of iterations in simulation instead of hardware synthesis. Then, as I said, we wanted to integrate with several frameworks. Initially, we did it with TensorFlow Lite. And without going into many details, the idea is that I have some DNN model, and at some point I have a layer, for example, this convolutional layer. I upload the layer, right, through what is called a delegate. This is a mechanism that TensorFlow Lite offers. And basically, then I upload this to our accelerator, and I can do simulation or real hardware execution. Here you see in between how we have this hardware synthesis or hardware generation. Okay, so this is basically what we did, integrating framework TensorFlow Lite with our methodology. Here, the problem we found is that we were not able to run emerging LLMs, and for that, we created a second tool, which is called SECDA-LLM, which essentially is the same as before, but instead of integrating TensorFlow Lite, we use the framework LlamaCDP, which is a widely used framework for dealing with many types of large language models. Okay, and again, this is the part that corresponds to LlamaCDP, and this is the part that corresponds to the SECDA methodology, which has, as before, simulation on the left-hand side and real hardware execution on the right-hand side. Right. So these are the tools that we have so far. Now, the problem that we have is, obtaining performance accelerators for a target FPGA is very time-consuming. So the process that I showed you before, an expert needs to be kind of iterating designs over designs, and this can be a very long process to actually get some design that meets the performance target we have. So then the goal was to automate this process, right? To enable an efficient and automated hardware design space exploration instead of having a person doing that. Well, we were thinking of several options to do this, and we found that LLMs can actually help a lot, because they can search the hardware design space, they can explore the hardware parameters, they can actually generate the accelerator designs. And the solution, as you can imagine, is our new tool, SECDA-DSE, which connects this automation power that LLMs provide with all our SECDA infrastructure that I have shown you before. Okay, our two tools that integrate the methodology. With that, we are going to significantly reduce the development time of new hardware accelerators, and because we are using open source LLMs, this will enables continuous improvement of the exploration process, particularly when we are targeting more complex or the most complex hardware accelerator designs. So this is how the design flow that we had before kind of changed when we consider our automated SECDA-DSE tool. So this blue box here in the past could be a person, right, a designer. So basically, in order to generate designs, accelerator designs, we have three inputs. We have some workload that would be a CNN, an LLM, or some other type of workload. We need to know what the target FPGA device when we want to deploy these, accelerate these models. And actually, and also we need to provide some directives for the DSS process. So what is the hardware architecture we are going to use? Is it going to be a systolic array or a vector mark? Are we going to use in the units? What is the data flow we are going to use? This type of kind of architectural directives. So with that, the human, or in our case, SECDA-DSE tool, will generate accelerators that later on we will evaluate on our tools. So as I have shown you before, we have for now SECDA-TF Lite and SECDA-LLM, but I put SECDA-X here, which means that we can develop other integrations with other potential frameworks like PyTorch, for example. Okay, so that's the motivation, the idea, and now we are going to go into the details of SECDA-DSE, and I give the word now to you.
All right. Hopefully you guys can hear me clearly. So Jose, yeah, thank you. Yeah, here's inside look into SECDA-DSE. First, I will highlight some of the key features of SECDA-DSE, and then further go into details in the upcoming slides. So SECDA-DSE is essentially a framework tool for developing new accelerator architectures and designs using LLMs to perform the design space exploration itself. And for this, SECDA-DSE takes in the target workload. So what kind of, maybe it's ML based, or maybe it's security, processing data from different sensors, whatever the workload, but we currently focus on mostly ML. Then take the target device that we have to use, and also some architectural directives, as Jose previously mentioned, as the input to the this overall SECDA-DSE approach. And then it produces accelerator designs and also performance data. The accelerator designs are obviously used as the user requires, deployed in real world scenarios. And then the performance data is used by SECDA-DSE itself to iteratively improve the approach. The key components of SECDA-DSE includes the DSE Explorer and the LLM stack. The SECDA-DSE approach is an iterative design process, which is enhanced by the performance data, which we evaluate using system C simulation and also using hardware generation using high-level synthesis and logic synthesis. Now we'll take a detailed look into the DSE Explorer, and after that LLM stack. So Jose, if you go to the next slide. Thank you. So the DSE Explorer is a component of SECDA-DSE that handles initial architectural template generation, and also we generate initial hardware datasets and data points to get that ball rolling for the LLM to fine-tune itself on. So the architectural templates are the baseline architectures that contain many hardware parameters or tunable knobs that we adjust as required by the user. And then a set of initial architectural templates have already been created by designers as an initial base for the LLM stack, but further architectural templates can automatically be generated by the LLM stack itself. With the DSE Explorer, we first design or select the initial architecture, and then we explore the possible parameters given the workload and the architectural directives. There are obviously several architectures already existing within the DSE Explorer, and they can be tuned as required by the user. Once we have this, we generate a subset of valid permutations of these architectures. So we call these design points based on the hardware device and the resources available on the target device, and also a learned cost model that's part of the feedback loop from the LLM stack, which we'll talk about in the upcoming slides. The permuted design points are then fed into our hardware automation system, which is where we perform high-level synthesis, simulation, and also logic synthesis to do a simulated evaluation and also a FPGA-based evaluation, and it will get us performance data that we can feed back into the LLM stack. These designs are initially evaluated quickly and packaged as a hardware data point, and also which is fed into the LLM stack, and also the architectural template itself, not the design points, but the templates itself are also fed into the LLM stack, so that it has a good context of what the initial architecture looks like. Note the hardware automation also takes into the target device and its resources available, which means that if a design, or rather if a permutation of a design is invalid given the device, this negative result is also fed into the LLM stack. So the LLM knows what not to generate as well. So yeah, Jose, if you can move to the next slide. Thank you. So here's the LLM stack. The LLM stack acts as the reasoning and the orchestrational layer, translating the user's desires and the evaluation feedback into designing the accelerator. We do this using some of the pre-existing SECDA tools. We have function calls that calls to the SECDA APIs and such, and it allows it to work in a smoother process. The LLM stack contains two main components, as you can see here, the retrieval augmented generation module, RAG, and the evaluation module at the bottom. So the RAG module uses the Ollama framework underneath to support open source LLMs. We want to keep it open source so that it's easy to quickly switch between models as the user's requirement changes. It also contains a fine-tuning module within that RAG module that is connected to a vectorized database that already has some information about the designs and pre-existing designs, such as the data points we generated using our DSE Explorer. And this vector database will continuously be updated through the feedback loop. And then, once we use this RAG module to generate designs, we also have an evaluation module that uses reinforcement learning to iteratively refine the accelerator design strategies based on the evaluation. So currently, the evaluation process does require a designer and tester to verify and validate the correctness of the design, but we plan on enabling the user of SECDA-DSE to provide test suits to verify and validate correctness automatically as well. So once that's enabled, we basically have a fully automated pipeline where the design's also validated and within this evaluation module automatically. And finally, for fine-tuning, we use low-rank adaptation, or LoRA, to enable our rapid understanding of the domain and adaptation while keeping the LLMs lightweight. Jose, if you can go to the next slide. Thank you. So for the LLM stacks, we have currently considered some models. In terms of the priority of why we selected the models, or what was the model selection criteria, essentially, was it supported by local inference via Ollama, the parameter efficiency and fine-tuning compatibilities, and suitability for hardware-aware reasoning, which obviously we need for generating hardware. We consider some of these models, so TinyLlama, 5, Mistral, and so forth. We have stuck with TinyLlama for now, as this is what's given us the best performance with our initial testing. But as the user's requirement changes, we can quickly just swap in whatever models that we want to run. Yeah. So additionally, we also looked into different prompting strategies to feed our user inputs. This is basically the architecture directives, workload, and target device, and also any additional user suggestions that needs to be taken into account when generating your designs. We initially started with direct prompting. Then we looked into instruction style based prompting, then just RAG based, and then just chain of thoughts. We finally realized we want both RAG to have that context of SECDA and previous designs, but also chain of thoughts to have more complex designs without having a larger model to work with. So we went with a hybrid RAG plus COT based approach for this. Yeah. And moving on here, we will present what the current progress and where we are in terms of all this implementation. So the DSE Explorer infrastructure that I mentioned before has been developed and integrated with previous, or rather relevant existing SECDA tools. So this means that we have enabled data transfer protocols such as the AXI protocol, System C simulations completely integrated. We have hardware and software profiling tools, and also automated high-level synthesis and logic synthesis, all within the DSE Explorer tool. Additionally, using this DSE Explorer, we have already generated an initial data set with a matrix multiplication accelerator architecture. This data set contains multiple design points with performance such as clock cycles and also hardware utilization metrics such as LETs, block RAM usage, DSPs, flip-flops, and such, which are common metrics for FPGA-based designs. The LLM stack infrastructure is also being developed, and we have fully integrated the processing pipeline, which includes the RAG right now, allows the users to generate the accelerated design with context aware of SECDA. Obviously, we have not fully fine-tuned this, and the idea is we continuously fine-tune this as we get more and more design points developed. And finally, we've also made sure that the context window which these LLMs work in have a good understanding of the SECDA tools. Specifically, we have a vectorized version of SECDA-TF Lite inside the context window. So for the next steps, the next steps include further developing and generating hardware data sets using the DSE Explorer to fine-tune the LLM stack. So the more different types of architectures, hardware data sets that we are able to provide, the better this process will work. And we will use the process to further fine-tune and design more architecture data sets. Additionally, we want to expose model context protocol libraries, so MCP libraries, which allows exact function calls to pre-existing SECDA tools. So this will make the LLM stack easily identify tools within the SECDA tools and call them directly and make the flow even more smooth or even smoother. And finally, we also need to do some testing of LLM generated designs and finish the feedback loop. So we want to test new architectures and validate them, adjusting the fine-tuning pipeline. For this, we plan to have someone that's inside that testing and evaluating loop initially, and then eventually we will automate this process as well. Finally, we are also preparing a paper for Insight workshop at Eurosys 2026. And yeah, with that, I will pass it over to Jose to conclude.
Right, so thank you, Jude. So some conclusions. So accelerating AI applications is becoming more and more important, and there are a few reasons for that: concerns on cost, power, security, and so on. So SECDA is a design methodology that reduces this development time of specialized accelerators, but is not enough, right? So because as we saw, we need to also explore the design space. SECDA-DSE Lite is an open source toolkit that improves the development of FPGA accelerators, particularly for the DSE Lite framework. SECDA LLM is the same, but considering the Llama CPP framework. And finally, SECDA-DSE extends SECDA by integrating this LLM-driven automation and hopefully reducing more the design time that we need for provide performance accelerators. So that actually was the presentation. So we are happy to take any questions. Thank you for your attention.